Hello everyone, today we will be talking about our notes for waves for AP Physics 1. Some of this vocabulary may be familiar from chemistry or our simple harmonic motion unit, and some of it is going to be new, so let's take a look. When we talk about waves in science, we're talking about traveling disturbances. Essentially, they are nature's way of carrying energy. We can categorize them into two main types, so mechanical waves and non-mechanical waves. Mechanical waves require a medium to travel through, and by medium, we mean material. So a mechanical wave has to have a material to travel through, otherwise it can't travel. The main example of a mechanical wave is a sound wave. So sound waves need something to travel through in order to exist. So sound waves can travel through air, obviously. They can also travel through liquids. If you've ever been underwater and tried to talk, you can still kind of hear it. It's just distorted. They can also travel through solids. So sound waves need some sort of material to travel through, while non-mechanical waves do not require a medium to travel through. And the main example of that would be an electromagnetic wave. In other words, light. So everything on that electromagnetic spectrum that you might remember from chemistry, ultraviolet, infrared, microwave, gamma, X-ray, all of those waves travel at the speed of light. Obviously, visible light is included in that. And none of them require a material to travel through. So if we think about space, you may have heard before or seen in space, no one can hear you scream. Well, that's related to the fact that there's no medium for sound waves to travel through if you are in empty space, so it would be silent. However, because light doesn't need a material to travel through, light is able to travel through empty space. Thankfully, because light from our sun is able to reach us through empty space and come to Earth. Another way we categorize waves is by labeling them as transverse or longitudinal. For a transverse wave, that means that the actual disturbance is perpendicular to the direction that the wave travels. So in order to help that make a little bit more sense, there's a GIF there. The transverse wave is moving to the right, and that red dot that's oscillating up and down, that's the disturbance. So you could think of this as maybe you have a string and you're making these sinusoidal type waves on a string. Well, the actual point on the string that's moving, that's being disturbed, would be that red dot. That's moving up and down, even though the wave is moving to the right. So that disturbance is perpendicular to the direction the wave is moving. And our main example of transverse waves will be electromagnetic waves, in other words, light waves. And you can see also that transverse waves typically look sinusoidal. For longitudinal waves, it's the opposite. The disturbance is parallel to the direction the wave travels. So you can see in the GIF there that maybe we have a slinky and we're kind of pushing the slinky instead of waving it back and forth. We're creating disturbances that are parallel to the direction the wave is moving. So the wave is moving to the right, and that red dot would be a point actually on the slinky, how it is moving. And you can see it's oscillating left and right, parallel to the direction the wave is moving. Our most common example of longitudinal waves are sound waves. So most of the vocab on this slide should be familiar to you either from chemistry or from our simple harmonic motion unit. So we have period, the symbol is capital T, the unit is seconds, and remember that is how many seconds it takes to complete one cycle. Frequency is the inverse of period. So the symbol for frequency is a lowercase f. It's measured in hertz. That's how many cycles are occurring per second. So our little equation there that we talked about last unit, period is equal to 1 over the frequency. They are inverse of each other. That is on your formula sheet for AP Physics 1. We also have amplitude, which is the maximum distance from equilibrium. The symbol for that is a capital A. It's measured in meters. For waves, this is a piece of new information. The bigger the amplitude, the more energy the wave has. So imagine I have a string attached to a pole maybe, and I'm holding the other end of the string, and I'm making transverse waves. So I'm making waves, and then I start moving my arm up and down even farther. I'm creating a bigger amplitude. I'm putting more energy into that wave. The waves are going to look bigger. They're going to have more energy. We also have wavelength, which is the horizontal length of one cycle. The symbol for that is the Greek letter lambda, and it's also measured in meters. So if you take a look at the diagram for the transverse wave, we have our amplitude. That's the same as it was for simple harmonic motion. We have wavelength, which we haven't really used yet, but that would be that distance from that crest to the next crest, or from that trough to the next trough, which you can't see in the picture. So we call maxima crests and minima troughs for transverse waves. The longitudinal wave is probably new to you. The wavelength is going to be the distance from one area of compression to the next area of compression. So instead of maxima and minima, we have areas of compression and areas of rarefaction. So you have areas where if you have a spring, it's being compressed. You have areas where the spring is not being compressed. And that's how that wave propagates through the material. This is the wave equation. It is on your equation sheet, and it should be familiar from chemistry. You might have used different symbols, but it's the same equation. So this equation says that the wavelength of a wave is equal to its linear velocity divided by its frequency. We will use this a lot working on problems. Thankfully, it's pretty simple, and hopefully you remember it, but if not, we'll get some more practice with it. This equation is probably new to you. This is specifically for waves on strings. So this equation solves for the speed of a wave on a string. So this could be you have a string attached to a pole and you're waving that up and down, or maybe you play a stringed instrument. Anything like that applies to this equation. So we have V equals the square root of the force of tension in the string divided by the mass of the string divided by the length of the string. I know this could be simplified as just force of tension times length divided by mass and then take the square root. There is a reason they write it like this, and that is because sometimes in a problem, you'll be given the mass per unit length of the string. I believe we will have a web assigned question that uses that, or at least an example. So if they're giving you the mass per unit length, let's say they say the mass per unit length of this string is 4 kilograms per meter. That means that the denominator of that fraction in the equation is just 4 kilograms per meter. Then you don't have to plug in a separate number for M and for L. So that's why it's written like that. I know it looks kind of weird. This is not on your equation sheet, but conceptually, let's take a look at what actually affects the speed of a wave on a string then. So imagine that I have a string, it's attached to a pole, and I'm just waving that string up and down, making transverse waves. So if we're asking ourselves what can affect how fast those waves are moving? Frequency, so that's how many cycles per second. If I change the frequency, will that change the speed of the waves? You might be inclined to say yes, because that means I'm doing more cycles per second, so the waves are moving faster. But if we look at the equation for the speed of a wave on a string, frequency is not in that equation. So it actually doesn't matter if I change the frequency, how many cycles per second the waves have, that actually won't change their speed as they move along the string. What about wavelength? So maybe I am changing the frequency and that's making the wavelength smaller or bigger. Will that affect the speed? Well, lambda wavelength is not in our equation, so that does not affect how fast the waves are traveling. Amplitude, what if I make my waves really big? I give them a really big amplitude. Will that make them move faster or slower? Well, amplitude is not in our equation, so it does not affect the speed. And lastly, we have medium, and by that I mean the type of string. And that actually does affect how fast the waves are moving, because mass and length are properties of our string. So that does change our medium. If I make my string heavier, that's going to have an effect on how fast the waves are moving. If I make my string longer, that's going to affect how fast the waves are moving. So the only variables that affect how fast our waves are moving on a string is our force of tension, the mass of the string, and the length of the string. So if you play a stringed instrument such as violin, guitar, let's use guitar as an example. The strings on a guitar have different thicknesses, which affects their speed, which is going to affect their frequency or their pitch. And they also, if you're trying to tune a guitar, you are changing the force of tension in the string. So you're changing the speed, which is changing the frequency, which helps give you the pitch that you want. One wave phenomena that you are probably familiar with in real life is the Doppler effect. So here is the fancy science definition. But really, it's something that you've probably experienced before and we can explain in different ways. But the Doppler effect is the change in frequency or pitch of a sound detected by an observer because the sound source and the observer have different velocities with respect to the medium that the wave is traveling through. So imagine you're standing on the side of the road, an ambulance drives by with the sirens on. It kind of makes that noise that we've heard before as it passes. And I'm going to try to make the noise, but it's going to be terrible. But it kind of makes noise like meow, something like that. It doesn't sound the same frequency the entire time it passes you. It sounds like it's actually changing frequency. Or even if someone honks at you as they're driving by, you'll hear that. So if you're standing on the side of the road, your velocity is 0, that ambulance is approaching you with some velocity and it's bunching up the sound waves in front of it. As you can see in the GIF, when that red part right there is highlighted, those waves are being bunched up, so they sound like they are a higher frequency. If you look at the waves to the right of that object in the GIF that's moving, those are spread farther apart. As the ambulance passes you and starts moving away from you, now it's creating the sound waves, but the sound waves are being emitted at different distances, spreading out because that thing's moving away from you. There's a great video if you go on YouTube and search Doppler effect. It's animated. There's a giant eyeball. It's fabulous. I'm going to link it on Google Classroom. They do a really good job of explaining it. Another example of Doppler effect is in astronomy, something called redshift and blue shift. So, brief explanation of that, because it is really interesting, is that we think of the Doppler effect in regular everyday life. We experience that with sound waves, but the Doppler effect also works for light waves. So the way that the Doppler effect relates to astronomy is that if you look at stars from Earth, it looks like they have what's called a red shift, that their light that they're emitting is shifting towards the red end of the electromagnetic spectrum, indicating that they are moving away from us because that's a lower frequency. Just like if the ambulance is going by you, when it's leaving you, it sounds like it's a lower frequency. So if we look at stars and everything, almost everything from Earth's perspective, it all has a red shift. All of the light that's being emitted as it moves away from us, just like the ambulance is emitting sound as it moves away from you, is shifting towards a lower frequency. So that makes it seem almost like Earth is at the center of the universe and everything is moving away from Earth. But in reality, if you were anywhere in the universe, everything has a red shift. Everything is moving away from everything else. And that has to do with that idea that the universe is expanding, which you might have heard before. Now, there are some things that have a blue shift that are actually moving towards us, but we don't have to get into that right now, but feel free to look that up. Very, very interesting stuff. And that's just an effect of the Doppler effect with light waves that helps us realize that the universe is expanding. So in life, waves are interfering with each other constantly. If multiple people are talking in a room, all of those sound waves are interfering with each other. If you have multiple light sources in a room, all of that visible light is interfering with each other. We have radio waves interfering with each other. We have a lot of different waves interfering at all times. So one part of this unit is wave interference. So this principle of linear superposition is essentially saying that if waves are interfering, if they're in the same place at the same time, we just add their amplitudes together. And whatever the resulting amplitude is, that's the new amplitude of the new wave at that moment in time, at that position. So we can classify interference into two types, constructive and destructive. So if two waves meet crest to crest or trough to trough, we would say that they are in phase or they are constructively interfering. If they meet always crest to trough, they are out of phase. They are destructively interfering. So here in the GIF, we have two troughs and then they temporarily add up. That was constructive because it was trough to trough, and you could see that the amplitude was twice as big. Here we have now we're going to have constructive again, two crests, and they temporarily added together to make something that had twice the amplitude. Destructive, we have a crest and a trough. They cancel each other out and then continue moving. So you can see that the waves are approaching each other and then they interfere So here they add together constructively, and then they just keep moving through each other. So let's take a look again. So here we have they're moving towards each other, constructively add together, and then they keep moving through each other in the way they were originally moving. And then we have destructive. So that crest is moving to the left, it's canceled by the trough, and it keeps moving to the left after that. In this GIF, the amplitude is always 0.5, so you can see when they add together, they should add together constructively to equal 1, which they did. And then since the crest and trough, when they interfere, have equal and opposite amplitudes, they completely cancel each other out. So we have an amplitude of 1, they move through each other. Then we have a trough of -1/2, a crest of 1/2, so they completely cancel each other out and keep moving through each other. And that's essentially it for the beginning of this unit. We're going to talk about other wave phenomena. We're going to look at videos, demos that I would normally do in class, but that's pretty much it for notes. So let me know if you have any questions.